Hi everyone. So in the next few videos we will discuss the last regularization strategy that we will study in this section, which is basically the class of what's called ensemble methods. And ensemble methods generally refer to training separate models and then taking their vote on the test data, right? So you have multiple models and then you train them independently, and then you take the vote, right? It doesn't have to be a majority vote, but in general you take the opinions of the different models on every test example. And the more diverse or independent or uncorrelated these models are, the better, because the less likely that they will make the same error, right? So think of the case where you have one example and there is a certain probability of error. Let's call it the individual error, the individual model's error, and every model has the same probability p of making an error on that example. If you have n models and you take majority, then it's roughly p to the n by 2, because you want at least half of them to make that error, right? So you will exponentiate the probability of error on every example. But that will happen if the models are uncorrelated, right? If the models are correlated, then they are more likely to make the same errors. And that's in general, the benefit of diversity, right? And but the challenge here is that achieving diversity is in many cases non-trivial, because all these models have to be well fit to the task to start with. All these models have to be high classification accuracy in case of classification, right? Or low reconstruction error in case of regression. So all these models have to be good, and at the same time you want them to be uncorrelated. Now the fact that you want all of them to be good on the training example pushes them to be correlated, right? And that's the key challenge with designing ensemble methods in general. Now there are two very common categories of ensemble methods. One is called bagging or bootstrap aggregating. And bagging basically consists of the following. You have a data set, you sample independently with replacement from this data set, right? So you create another one. So let's say I have a data set with 10 examples. I take one out of the 10 examples with equal probability. And then I take another one of these 10 examples with equal probability. It doesn't matter what the first choice was. So I can repeat the same choice. And I create a new data set sampled with replacement out of the original data set of 10 examples. And then I create another data set sampled independently with replacement from the same original data set, and so on. If we do that, and if each of the data sets have the same size as the original data set, then each separate example will be included roughly with probability 2/3, right? So let me, so you have 2/3 of the examples will occur at least once in the selected set on average, right? So there will be an overlap between the selected sets, but not identical, right? And there is a nice figure in the book, which is figure 7.5, and basically it refers to an example where you have an image of a 6, an image of an 8, an image of 9, 3 digits. And when you do the bagging, sometimes you will have larger weight to images of 6 and 8. So that model trained with this data set will learn that the 6 is distinguished from the 8 through the 8 is distinguished from the 6 by having the upper circle, right? So you have 8, 6, and 9. So when I do this sampling with replacement, let's say in one data set, I have higher weights to the 8 and the 6, right? So in that model trained with that data set will learn that the 8 has the upper circle, and that distinguishes from the 6, right? Another model trained with higher weight to images of 8 and 9 will learn that the 8 is distinguished from the 9 through the lower circle, right? Now, when you take a combination of these models, or when you take the opinion of these models, then it's likely that when they both agree that the image is an 8, that it's really an 8, right? And that could deliver better performance than one model that's trained on all of them, right? Because one model that's trained on all of them can fail to identify the distinguishing aspect of both circles of the 8, because the lower circle is shared with the digit 6, the upper circle is shared with the digit 9, right? So in general, when you do the sampling with replacement and you train the model with different data sets, even though these data sets are drawn from the same original data set, then you focus, each model will focus on different features to extract. And then that will create diversity among the model's opinions, right? Even if the data sets overlap, or even if they are the same data set, there are many variations that could distinguish or could be sources of diversity between the different models. For example, as we'll study in the next section, usually initialization is done through a random process, right? So, or a random number generator. So the weight initialization can be different between the different models. The selection of many batches, and that also will be studied in the next section, could be random. So I randomly select many batches for every training iteration. I randomly select training examples, all right? And that could also add an effect similar to the effect of sampling with replacement. The hyperparameters could be different from one model to the other. So maybe the learning rate is different. And also non-deterministic implementations of other factors, like for example, random noise injection. Even though the noise could have the same distribution, the realizations could be different from between the different models, right? So in general, all these sources of diversity can make the models make uncorrelated decisions. So that's basically the main idea behind bootstrap aggregating or bagging. Right, so bagging is an abbreviation for bootstrap aggregating. Usually the word bootstrap is used in statistics to refer to that process of sampling with replacement, and aggregating because we take the vote, we aggregate the opinions of the outcomes of the different models that we use. The other category of methods that's classified as ensemble methods, but not necessarily a regularization strategy, refers to what's called boosting. And boosting refers to adaptive training, using either changes to the model itself or the training set. And so that's different from bagging, right? So bagging is adding diversity a priori at the start. Boosting is doing it adaptively while training, right? So depending on the outcome on the training iteration so far, I could decide on the next mini batch to choose, or I could decide to make decisions about the model itself, whether adding or removing units, or maybe changing the architecture, right? Or adding layers or removing layers, and so on. So this adaptive training procedure is usually referred to as boosting. It's also an ensemble method, but it's not necessarily a regularization strategy. And remember, the definition of regularization strategy is whatever strategy whose objective is to improve the generalization performance or the validation or the testing error, and not necessarily improving the training error. It can happen as a byproduct, but it's not an objective. Boosting is not necessarily like that. Boosting can be for minimizing the training error as well. So it depends on the boosting method, but it's not necessarily a regularization strategy. Bagging is definitely a regularization strategy. Both of them can be classified as ensemble methods, as they involve different models, whether the models are determined like in bagging prior to training or adaptively while training. Thank you.